part 3 of 3 for functional MRI. All right, so now we're getting into imaging the brain's physiological response. Let's see, we're going to build on what we talked about last time. So last time we talked about how, in the last few videos, we talked about how what the scanner is. It's a big magnet, and how it lines up all the protons and then pulses them with radio frequency waves and then detects their very quiet echoes back. And so now we're going to go from that into how we can use this technology to characterize the physiology of the brain, the blood flow response of the brain when there's a cognitive event that has a corresponding neural event, and we can see the response of the brain's vasculature to that. And this is in large part possible because of researchers like Seiji Ogawa. So he and his team were looking for a way to examine brain physiology using MRI, and they showed that deoxygenated blood can be used as what they called a naturally occurring contrast agent for MRI, which means that you can tell that the signal strength changes based on the proportion of oxygenated versus deoxygenated blood at a given point in the brain. And this all hinges on the metallic properties of hemoglobin, a metalloprotein embedded in red blood cells. So just to zoom out a bit, this idea of hemoglobin. So we've known about the hemoglobin molecule since Linus Pauling characterized it. The idea is that this molecule lets the body carry oxygen from the lungs to the tissues of the body that need it, including the brain. When hemoglobin is oxygenated, it has no magnetic moment. It's diamagnetic. When it's deoxygenated, when it's delivered its oxygen molecules to the tissue, it becomes paramagnetic. So it's got unpaired electrons and a significant magnetic moment to it. If you think about when oxygen binds to iron, it gets rusty and it also loses its magnetic properties. So this is kind of a similar thing. We've got a teeny little bit of iron that has oxygen that can bind and unbind to it. And one hemoglobin molecule can carry up to 4 oxygen molecules. All right, so now what we're building up to is this idea of a blood oxygen level dependent signal, the bold signal. So in the previous video, we talked about how you pulse the brain with radio frequency and the local protons are precessing in synchrony. They're in phase with one another, which yields an induced oscillating current on your receiving head coil. Now there's this idea of something called T2 decay, which describes the rate at which the signal is lost as the protons drift out of phase with one another. So like how long you get that resonant signal coming from the tissue. So the idea is that the magnetic properties of deoxyhemoglobin mess with all the protons that are precessing in local tissue because they change the local magnetic field strength. So you have these little magnetic molecules of deoxyhemoglobin, and they're actually, like we said, the Larmor frequency determines the rate at which protons precess. And so if you've got a tiny little magnet next to some of those protons, it's going to change actually the rate at which they precess, and they're going to get out of sync with all the other protons, and they're not going to give as nice a signal. And so the idea is that the local magnetic field strength affects the local precession frequency. And when blood is deoxygenated, the protons drift out of phase more rapidly, so the signal goes away more quickly. And when blood is oxygenated, the signal persists longer. You get a stronger signal. So Thulborn et al. 1982 showed this difference using vials with different proportions of oxygenated and deoxygenated blood. And they also found that the effect is stronger at higher field strengths, so like 1.5 Tesla and like the 3 Tesla scanners that get used most often in research. So as the brain's vasculature delivers oxygenated blood to an area and drains away the deoxygenated blood, the local signal strength increases. So I took some figures from Ogawa et al. So Seiji Ogawa's one of their original studies characterizing how the oxygenation versus deoxygenation affects the imaging of the vasculature. And so as to not, use copyrighted images, I just drew my own little versions of them using a paint program. So this is what you'll see if you go find this article. It'll look a lot like this, except it'll look like an actual brain instead of my drawing of it. So what they did was they had a rat, and they had an animal scanner that they could use, a rat breathing pure oxygen, and this is a coronal slice of the rat brain using something called a gradient echo image. And we don't have to worry about gradient echo versus other kinds of images for our purposes here. It's just one way of basically tuning the scanner in order to get good images out of it. The important thing here was that they did a contrast with a rat breathing 20% oxygen. So we have pure oxygen, 20% oxygen. And so 20% oxygen is the normal amount of oxygen in air. And the same imaging parameters were used, but now all of a sudden you could see the vasculature all over the brain become darker. So the deoxygenated hemoglobin, as it's getting drained away by the vasculature, that's where there's a drop in signal intensity. And so the idea was, the proposal was that, okay, so we're seeing a decreased signal for deoxygenated hemoglobin and enhanced wherever there's more oxygenated blood, so we can use this to monitor regional oxygen usage in the brain. Okay, so next up is, actually I'm going to bust this into pieces because that's 7 minutes already, and I'll just add an extra part to this series, and that way the videos are more manageable chunks. So I will see you soon.